Let's talk now about porosity, permeability, and aquifers. This is a high magnification picture of sandstone. So this says this is 500 microns here. That means that double that length, this is 1 millimeter. So this is way zoomed in, right? 1 millimeter is like not even the width, or around the width of a fingernail, maybe slightly more than that. But just to think that this is a pretty zoomed in picture of the sandstone, right? Each of these is a sand grain. We normally think, okay, sandstone has been lithified, it's solid rock, but it still has pore spaces colored in here in blue. All rocks have pores in between those grains. And so here we can see that this particular sandstone has a lot of pores in it. So you could, in principle, fill that sandstone. If it's in the zone of aeration, it's going to be filled with air and water. But if it's in the zone of saturation under the water table, those pore spaces are going to be filled with a lot of water in the case of this particular sandstone. We can talk about the porosity, P-O-R-O-S-I-T-I-Y, excuse me, as being the amount of pore spaces in a rock. And so there are various things that can change a rock from being more or less porous, vice versa, various things that can affect that. So in a sandstone with relatively little cement, you're going to have much more pore space, a higher porosity, than in a sandstone where a lot of those pores have been filled with cement, right? And remember, those cementing minerals can be things like silica, or it can be calcium carbonate or hematite. So various minerals can fill those pore spaces and cement the rock together. And the more cement there is, the less porosity you're going to have. If your sandstone is well sorted, the grains are all the same size here, then your pores can actually be larger than if you're poorly sorted, because in a poorly sorted sandstone, there are particles that can fill those pore spaces. That's what we see in this diagram over here. A poorly sorted sandstone is less porous. And then you can have rocks that have various amounts of fractures in them, right? So under tectonic activity, you might cause rocks to fracture in a brittle way. And so we can get fractures forming in rocks like shale that increase the amount of pore space. If those shales were unfractured, they would actually have less pore space in them. Porosity is not the only thing that we need to think about when we're thinking about groundwater motion. We also have to think about permeability, which is related to porosity, but it's not entirely the same. Permeability refers to how easily or quickly water flows through the pore spaces. So in a situation where you don't have any pore spaces at all, you're non-porous, you're definitely going to be non-permeable. But you can have a situation where you have a decent amount of pores, but if those pores aren't connected to one another, then you're going to be relatively non-permeable. Whereas if your pore spaces are more connected to one another, you will be porous and you will be permeable. So permeability really only refers to how fast water flows through, and that's related to how connected the pore spaces are. So here's our example where we can see a high porosity, low permeability rock where the pores are really not very well connected to one another. There are small cracks, and so there's probably a little bit of permeability, but it's low. It's not zero, but it's low in these cases. Whereas if you were to break open some of those pathways just a little bit, you would still have about the same porosity, maybe slightly more, but you would suddenly be very high permeability because water can very easily flow in between all of these pores. To get a sense of how fast water can flow through here, we can think of sort of a moderately permeable sandstone. And water in there will flow at a few centimeters every day, pretty slowly. If instead you had loose gravel, not cemented together, relatively loose, underground, that water could flow maybe 10 times faster than that on average. And that's because, not because there are more pore spaces in the gravel, but because those pore spaces are better connected. So it's the permeability that governs the speed of groundwater flow. And permeability is sometimes related to porosity, but it's not entirely 100% the same. So let's go back and think about something that we had talked about before, which was the term aquitard or aquiclude. So an aquitard or aquiclude refers to a layer of rock that is low permeability. That's all that matters. It could be low porosity or it could be high porosity, it doesn't matter. But if the permeability is low, then any water percolating downward is going to be unable to percolate through the aquitard. And as a result, you can have aquifers those are bodies of water underground forming above that aquitard. So over time, if you rained enough on the surface, you would form what we call an aquifer, which is just an underground body of water. Those aquifers can either be unconfined, open to precipitation at the top, or they can be confined. And in the case of confined aquifers, they are confined by a layer of impermeable rock above them. How do we even get water into one of these spots? Well, somewhere further along, that aquitard must end. And we must have water entering it somehow. Could be further upslope, could be in the mountains. But a confined aquifer is only recharged by water that can pass around that aquitard somehow. So some written out definitions here. Aquifer is a porous and permeable. Porous because it has to contain water, and permeable because that water has to be able to move through it. Water saturated zone of rock. So it's a body of water under Earth's surface. Unconfined aquifers are those with no aquitard above, and they can recharge directly from precipitation, whereas confined aquifers, there is an aquitard above them, and they can only recharge where that aquitard is absent. And the aquitard or aquiclude is the name for a non-permeable layer of rock that acts as a barrier to groundwater flow. So taking a look at that again, we can see that the unconfined aquifer can recharge directly from the precipitation, and the confined aquifer must be recharged from somewhere else. Here's a more complicated example where we see a perched water table, an unconfined perched water table, sitting on top of an aquiclude, and then where that perched water table meets Earth's surface, a spring comes out. And that is water flowing out of that into the spring and then flowing downslope as surface water. And it's that lens of an aquiclude, in this case, a mudstone that's not fractured, so it's not very permeable, that forms that barrier to groundwater flow. In this area, you would say that the aquifer is unconfined over here and is confined underneath the aquiclude. It's a particular type of well that exploits those confined aquifers, that actually flows without having to do any pumping. And these were very unique places that people would like to farm near because it was very easy to tap them for water, because you wouldn't need to put any extra energy in to get water out. You wouldn't need to dip a bucket down or anything. By drilling a hole to make an artesian well, you actually get water to flow without any pumping. And that's because they are working out of a confined aquifer that is recharging from somewhere far upslope. And because of that, the water pressure is pushing downward on it, such that if it could, it would flow out to about this height here. We can call the pressure surface. And as you get further and further away from the source of that water, the pressure surface goes further and further down. But if you're relatively close to that mountain range where it's recharging, you can drill a well and the water will try to flow upward until it hits that pressure surface, which is just a surface that where the forces of gravity pushing down on the water here are balanced. In these cases, A well that was drilled up here instead would not be a flowing artesian well because the top of it is not below that water pressure surface. The thing to remember here is that artesian wells are exploiting confined aquifers only. They don't work in unconfined aquifers because there's nothing putting pressure on that water. Here's a map of the types of rocks that contain aquifers in Tennessee. So for the most part, we have some sandstone aquifers, we have a lot of carbonate aquifers, and then we have some unlithified aquifers in things like alluvial sand or other tertiary sand, which means, is deposited in the last 60 million years or so. But those are unlithified. So you can have an aquifer in a rock or in unlithified sediment. And in Tennessee, those tend to be sandstone or especially carbonate. So things like limestone. So in Knox County, we are working out of a carbonate aquifer. Groundwater is related to hot springs. And we've talked about this a little bit before, but groundwater that percolates downward and reaches an area that's close enough to magma will start to heat up. And it doesn't need to be right next to it. It can be a few kilometers away from that magma, but it needs to be near an underground heat source that causes that water to turn to steam. And as it turns to steam, it expands and it forces more water out of the top of a system of cracks in that rock, where you can have either a hot spring just sort of gently bubbling out onto the surface, or you can have a geyser, which is sort of repeated turning of water into steam in particular pockets and then exploding out all at once. So here's an example of a geyser from Yellowstone National Park going off, and it's going off because water in the subsurface expanded and got pressurized and pushed out of the surface. We can see a sequence of how that geyser erupts in this schematic diagram here, where we have a cavern that gets filled with groundwater that percolates into it. And as that groundwater heats up, it eventually turns to steam, and that steam is now a gas, and that gas is pressurized because it's pushing outward. The volume of a gas is much higher than the volume of a liquid. And so it's pushing and forcing to try to push that water, and it finds an area where it's able to flow out, and it flows outward onto Earth's surface as an eruption of a geyser. So all that steam erupts, and then these spaces in here are left empty for water to recharge again. And the cycle continues. Hot springs and geysers are mostly concentrated in areas where there has been some tectonic activity in the past. And so it makes sense that there are a lot out west, at least up to the edge of the Rocky Mountains, where there's been some tectonic activity, some magmatic activity, and we see a whole bunch right around here. This is the Yellowstone hotspot. So it's associated with a very high density of hot springs. But there are some in the East Coast too. In older fault systems, like in the Smokies, especially in Virginia, and all the way down into Georgia, and there are a couple dotted through Arkansas and some very old mountain ranges there.